Alright, Military Handbook 1005-16, Section 9, Effluent Disposal Reclamation. Alright, 9-1, Introduction. Two main means of effluent disposal, reclamation, surface water discharge, land application, rapidly grow technology for the disposal reuse include the Groundwater Recharge, Aquifer Storage, and Recovery of the Water Environmental Federation, MOP 8, Chapter 20, covers the applicability, treatable pre-treatment methodology, design, regulatory issues involved with the land application, the handbook that covers the design and surface water with the discharge outflows, and discuss with the emergency groundwater, the recharge and aquifer storage and recovery technologies. 9.2 Surface water discharge or outflow of the permit compliance with the can be facilitated with the duty selection with the design for the surface water outflow with the oven, and we receive the water is already dictated with the location of the FOT existing facilities. In some cases, the outfall can be relocated, modified, and improve the stability of the FOTW. Remain the compliance with the majority of the process. James, the section review the general issue of the consideration about the surface water outflows. Additional design references include mixing inland with the coastal waters, the Fisher ETL in 1979, wastewater engineering, treatment, disposal, and reuse, Metcalf and Eddy in 1991. Outfall location. Surface water of the discharge cannot be impaired with the receipt of the water capability below the state water for the quality standard for the typical to be determined through the waste load allocation study. The study evaluates the assimilative of the capacity of the water body of the receiving the water for the little flushing like lakes, of which are dominated and fluent by like small creeks and any only used over the last alternative. If a large water body with a dilution capability of the nearby, then it may be necessary to pipe the FOTW effluently into this large water. Know that new open oceans outfall for the Atlantic Ocean, Gulf of Mexico, highly discouraged by the Environmental Protection Agency after the general location of the outfall of the receiving water has been determined by the more specific design details evaluated. 922 of the outfall configuration. The configuration of the outfall pipe itself sometimes be changed to improve the pipe permit the compliance with, for example, the wastewater load application determines the fluent dissolved oxygen depletion. A cascading structure of the long steam bank can be used to satisfy the sum of the effluent oxygen demands. However, the often overfall is emerged away from the shore. If the pipe has a simple opening and at the back, better mixing can be attained with the installing with the diffuser inside and induce jet flow through one or more ports. The permanent should be included with the dilution and mixing to help the FOTW to achieve compliance for the new discharge. The same issue that may arise. The regulatory agencies will often have to major role in requiring the level of dispersion mixing necessary to reduce the potential environmental effects. Size and capacity. Design outfall should be conducted for a peak hour flow with the maximum anticipated shore of the receiving the water. With the receiving water is entitled and both of the high and low conditions should be evaluated. The outflow pipeline should be followed with the typical pipeline design guidelines for these type of structures. If the diffuser is installed, then special mixing models are used to select the power port size spacing with the pipeline. Typically have the flow of less than 10 feet per second. Differ port receiving the velocity of greater than 10 feet per second to achieve the jet mixing. The ports of the diffuser should be directed slightly upward so the flow does not impinge the water of the bottom of the body of the bottom. Port sizes should be 2 inches in diameter or greater to ensure the port will not be clogged with scaling or barnacles. Pipes can be made of various materials. Most of the outfall of the construction daily to the either ductile iron or plastic corrosion protection should be considered with the applicable. See the section 12. High density polyethanol hot pipe is often used for the submerged outfall if they are buried. Note that the HDP or the high density polyethanol pipe is specified in the outer diameter, while other types of plastic iron pipe are specified in the inner diameter. 924, outfall depth. The outfalls are submerged to avoid visibility and interference with the water body. Usually the outfalls are located away from the shoreline to minimize the contact with the shallow water bathanic organisms to provide better mixing as long as they do not interfere with the dredge and navigation channels. The deeper the outfall, the better the mixing. The outfalls need to be at least 8 feet deep to provide mixing opportunity to consider existing pipeline to beat water. If existing outfalls in shallow water, if have the permanent compliance issues, and they could be extended and shelf outfalls do not need to be modified. Regulatory authorities do not require outfall protection. Outfall pipelines should be anchored in place of the receiving water to prevent movement. Anchoring is often accomplished by bearing the pipeline and using the 90-degree elbow at the end of the surface. The outfall, multiple port outfalls have risers along the pipeline extending above the buried pipeline. The piers can also be used to support the outfall for the sum of the distance of the shoreline. But the pipeline exceeding beyond the pier to avoid the public contact need anchoring. Sometimes the pipes have the color type of the concrete weights that can be particular partially submerged with jets to anchor the pipeline. Sometimes the riprap that used with the stabilizer provided with the base for the pipeline sitting on the bottom grade above the grade. Pipelines can experience the sedimation scores first, of which needed to consider for the designer. Addressing the COE requirements today for the ownership of the water body design, the pipeline is too shallow. It can interfere with the boat traffic, and some regulatory agencies will allow the shallow outfall to be marked with lighted warning buoys or other by means. Transition zones neither the shoreline will be need special consideration during design construction, since they are often most environmental sensitive to the publicity via visible areas. 9.3 Groundwater Recharge. Groundwater recharge can be accomplished by using the infiltration basins through the underground injection wells. 9.3.1 Infiltration basins. Artificial recharge with the groundwater can be achieved with the infiltration basin with the soil, but they're impermeable with the sufficient portion of the aquifer is unsaturated, but the aquifer is unconfined. 9.3.1 Applications guidelines. Design of the management infiltration basin should be adapted to the local conditions, water quality, climate, soil hydrogeology, environmental constraints, aspect with the consideration, including water depth in reference to possible increase of the infiltration rate, the length of the flooding in the dry period, the frequency of the cleaning basins, sedimentation. Also, selection between the basins with the stagnant water when the fine materials were able to settle. Basins of flowing water while the fine materials are kept and suspended because of the turbulency should be made. Chemical and biological water quality performance parameters of fluently water need to be considered. Also consider the change of water quality as the water moves through the Verdosis zone and aquifer. The potential leaching with the tracing elements for the Verdosis zone and the groundwater monitoring program may be required by federal, state, and regulations depending on the quality of the fluent discharge for the basin. Proximity with the public drain water wells may also affect the groundwater monitoring, requiring referred to artificial recharge for the groundwater. A.I. Johnson and Donald J. Finlayson, eds. 1988. General design guidance. Our infiltration system for the artificial recharge of the groundwater should consider the number of the basins and cave for the hydraulic loading rates need to be maximized depending on the topographical such of the basin can have much of a surface of a quarter to 25 acres or more. Each basin requires own water supply drained so that it can be flooded, dried, and cleaned according to the best schedule for the flow of the basin. The basin should not be placed in series so that the outflow of one of the basins is inflow for the lower basin because the such system of the basins cannot be dried and cleaned individually. Design overall system to allow any of the basins to take out the surface of sufficient drying period. The first few basins are sometimes designed to be used with the pre-sediment basins. Some basins, particularly deep or low infiltration basins, should be designed for the separate drainage system which allow the quick dewatering from the dry and cleaning of the structural basins, horizontal graded bottoms to prevent the low places where the water can stay in long periods and interfere with the infiltration, recovery, and cleaning operations. In cases where the groundwater is mounted, groundwater mounds could rise above the bottom of the infiltration facility. The basin should be laid out to minimize the inundated area. The groundwater's flow media modeling usually readily available to model the MO such as mod flow may be required to evaluate the potential mounding effects during the design. The basins should be small, large, and narrow. Adjacent basins should be flooded at the same time. Refer to the EPA 625-181-013A. Process designed for land treatment, municipal wastewater supply, supplement, and rapid infiltration overland flow. 932 Injection well. Many of the successful injection well systems inject and moderate with a highly treated wastewater that have been constructed across the United States. Many of these systems are located in California, Texas, and Florida. Injection wells are characterized by under 5 general categories: Class 1, Class 2, Class 3, and Class 4, and Class 5. Based on the type of the waste stream, well design use wells hydrogeological characteristics at the injection site flight. Florida's injection well classification, which are modeled with the federal classification represented with the Table 12, refer to the Groundwater Recharging Using Water Impaired Quality National Research Council, 1994. Application guidance. Rechargeable wells are potentially applicable to the area with the surface of the soil, but they're not available to land. It's too costly for the wastewater flow with excessive wastewater quality and unacceptable infiltration basin. Drinking water wells are in close proximity with the wastewater treatment facility, and Verdosis zones are a restriction layer with undesirable chemicals that could leach out. For these conditions, among others, injection wells are an option. Domestic industrial wastewater injection wells typically recharge brackish and saline water aquifers or aquifers, others poor water quality. Injection wells are made to be used to develop a barrier of the saltwater intrusion in coastal areas using highly treated wastewater to be used in the underground injection underground various levels of pre-treatment up to including advanced wastewater treatment process. Interaction between the injection water and these native groundwater include full characteristics of each of the should we well understand the characteristics typically based on federal and often state drinking water standards. 9322 General Design Guidance. Several general guidelines criteria should be evaluated when designing injection well with a system before concentration. For completion, data details include type of the casing, material of the well screen, if in use the carbon steel, stainless steel, polyvinyl chloride, approximately casting steel, settings depth of the casting diameters, generally designed for the fluid velocity of 8 feet per second. Necessity of the tubing and packer, whether well is screen or open borehole, pump station design, well pumping, wellhead piping, and prudency, including flow and pressure monitoring, equipment, hydrogeological drilling and testing program to collect analyzing aquifer data, packer testing and coring and specific gravity testing, geophysical logging program, and water quality sampling. Alright, Table 16 shows the classification injection wells. 1. Wells are used to generate hazardous waste and owners operate with a hazardous waste machine facility inject the hazardous waste beneath the lowermost formation containing 1/4 of the mile with well bore underground surface of the drinking water. 2. Other industrial municipalities, public or private owned disposal wells which inject fluids beneath the lower formation containing within 1/4 of the mile well bore underground source drinking water. 2. Wells that inject fluids where they are brought to the surface in conjunction with the connection with the conventional oil and natural gas production and may be commingled with the wastewater for the gas plants, which are an integral part of the production operation. Unless the waters are classified as hazardous waste at the time of the injection for enhanced recovery of the oil and natural gas, for storage of the hydrocarbons if they are liquid and standard temperature for the pressure. 3. Wells that inject the extraction minerals include mining of sulfur and fractious by a fractious process. Solution mining of the minerals. Solution mining of the material minerals includes sodium, chloride, potash, phosphate, copper, uranium, and other minerals that can be mined by this process. This is 3. Alright, 4. Well used generators hazardous waste with radioactive materials by owner and operators, hazardous waste management facilities by owners and operators with radioactive waste and disposal sites. Dispose of the hazardous waste and radioactive waste into the above the formation, which 1/4 mile of the well contains either the underground source of the drinking water or expected aquifer. These types of injection wells are abandoned nationwide. And 5. Injection wells are included in Class 1, 2, and 3, and 4. Class 5, which are grouped in expected quality of the injection fluid, include Group 1. Air-conditioned return flow well to return any aquifer water to the heating, the cooling, air-conditioned supply well, a heat pump, the return flow well with the injected water containing the additives into the same permeable zone from what is withdrawn constitute a closed loop. B. Cooling water return flow wells used the injection water previously used in the cooling. Group 2. Rechargeable wells used in replenishing, augmented, storing water, aquifer, saltwater intrusion barriers wells used in injecting water into the freshwater aquifer to prevent intrusion with saltwater into the freshwater. Our Class 5 continued subsidence control wells not used for the purpose of the oil and natural gas production used to inject fluids into the zone. Does not produce oil or gas to reduce, eliminate substances associated with overdraft in the fresh water. Connector water wells used for the connection of two aquifers to allow interchange of the water between the aquifers. Group 3. Wells that are part of the, Class 5 Group 3. Wells that are part of the domesticated tree system, swimming pool, drainage wells, receiving waste that have been opened with the bottom sometime with the perforated side, but the rules do not apply with the single-family residential waste disposal system. Wells used to inject spent brine into the same formation for which it was withdrawn for the extraction of the halogens in their salt injection wells used with experimental technologies. Group A, dry wells used the Group 4, Class 5, Group 4, and dry wells used for the injection waste into the subsurface formation. Sand backfill wells to inject mixture of water and sanding and tailings and other solid within mined out portion of the subsurface mines. Wells other than Class 4 used in conjunction with the radioactive provided with the concentration of the waste does not exceed drinking water standards contained in Chapter 6255 Florida Administration Codes. Class 5, Group 4D, injection wells used with the suit recovery phosphate, uranius, sandstone, clay, sand, and minerals extracted by the borehole slurring mining method. Class 5, Group 5, draining wells used to drain surface fluid, primarily storm runoff at the lake level and gravity flow into the subsurface formation. Class 5, Group 6 injection wells associated with the recovery of geothermal energy by heating the aquaculture production, electrical power, or other wells. Classification permitting the requirements injection well, which will likely require the complete with the characterization of wastewater to determine the aquifer system acceptable to underground injection, the groundwater monitoring program, if applicable, to demonstrate the compliance with the federal underground injection control or UIC rules. The program includes several monitoring wells complying with the various depth design of the monitoring, possible mitigation of injection fluids. G. Additional design consideration, including high well level alarm, continuous head monitoring, downhole flow metering per individual well, potential groundwater geochemical interactions. 9323. Design details determined during the installation. Several final design details are determined during the well installation include the following. Type of the quantity of the cement to be filled in annular space to prevent fluid migration, final casing, setting depths, information determined in any state of the federal relief mechanisms needed to operate the system, aquifer exemptions, operation, testing of the injection system to obtain the appropriate operating permit, state and federal UIC rules, including the strict compliance with the provide maximum assurance that the underground source of the drinking water, defined as is most criteria, the aquifers contain 10,000 milligrams a liter less total dissolved solids, will not be negatively impacted underground injection of the domestic water. Or you reference to assist the wells design criteria for the groundwater wells, UOP Incorporated 1975. 9324. Operating consideration. The step of the operation consideration of designing the injection well with one of the possible concerns with the injection well, they will be clogging with the aquifer around the well, especially with the borehole interface between the gravel package and if you use the borehole wall, the suspended solid that accumulate with the bacteria growth intent for the concentrate of the air, the other process that can decrease injection rates in wells and participation with the calcium carbonate, iron oxide, other compounds, aquifer dispersion, swelling with the clay and air binding. Injection wells are more vulnerable to clogging than surface infiltration because the infiltration rates are much higher with the clogging effect for the remediate with several methods, including periodic pumping of the wells, reverse the flow of the potential dislodgeable clogging materials, acidization of the injection well. When the wells are to be pumped, the initial flow of the typical brown orders is recycled through the treatment plant with the pumping schedule is required range from 20 minutes per day to several times per year. If pumping does not restore the injection rate, the redevelopment of the well may be necessary. The best strategy for the dealing with clogging is to prevent it from proper treatment of the water before injection. Limiting the load of the suspended solids, assimilable organic compound nutrients, and the nitrogen and phosphorus and microorganisms that may reduce the potential for clogging, chlorination of wastewater, and may be effective at minimizing microbiological activity. Acidization of the wells, the process involved in injecting concentrated acid solution of typical hydrochloric acid down the well, shutting in the well. Shutting in the well, allowing the acid to react with the formation of the back flushing of the well with the continuous injection. Active acidization is a very effective method of restoring injection capacity with the carbonate aquifer system. And other operational consideration, mechanical integrity of testing of the wells, which include the internal MI or mechanical integration demonstration to show the fluid movement of the occurring due to leaks in casing. The external mechanical integrity demonstration to show the annual fluid movement occurring around the casing installed. Most of the injection wells that require the mechanical integrity demonstration every 5 years at the minimum. The Groundwater Protection Council's Class 2 injection well mechanical integrity testing basic training course of the Groundwater Protection Council in 1994. Mechanical integrity design criteria for the available technology wells should be designed to allow the effective economical well rehabilitation testing activity to provide form, routine, and permit driving basis. Art 9.4 Aquifer Storage Recovery. The application considered for the technology required with the command of the high rate headquarters with approval of the Aquifer Storage Recovery or ASR stores water in the suitable aquifer that through the well during time of the excess water is available. The same water is later recovered through the same time of the well during times when it is needed. The most aquifer storage recovery applications in operation today for several seasonal long-term emergency storage potable drinking water. The aquifer storage recovery system using treated wastewater known as exists. However, the main systems of Florida are various stages for the development of federal regulations for the reclaimed water. The aquifer storage recovery system are pending, although several states with the program, including Florida, including the final stage of development. In fact, Florida reuses the rules currently under the provisions encouraging promoting reclaimed water, aquifer storage recovery programs, or provide seasonal storage with the increasingly available commodity, allowing wastewater treatment plants to operate with more effectively manage their reclaimed water system. For the groundwater recharge wells and guide aquifer storage recovery, David Pine, 1994. Application and guidance: the high quality remainder of reclaimed water may be stored seasonal and brackish aquifers later recovery. Alright, to meet the irrigation of the other demands, the aquifer storage recovery technology that were stored in the subsurface at the later date, possible aquifer storage recovery, the applications include storing and recovering the water means diurnal variation supply with the demands acting on the reclaimed with water to meet the demands during the extended drought periods when the quality of the water is not acceptable for reuse application. The strategical locating of the aquifer storage recovery system is the location where the flow of the pressure constraint inherent with the reuse system. The reclaimed water stored in the aquifer storage recovery system could blend in brackish water resource under certain application to maximize the use of the fresh water. Brackish water in an area with limited with the water resource with additional aquifer treatment can occur under the certain hydrogeological conditions which may enhance the reclaimed water quality. The advanced treatment of the storage and recovery of the water can allow the wide range of applications, including indirect potable reuse of the water, treatment of the water, drinking the water standards. Under the most applications, the aquifer storage recovery provides the additional reliability, operational flexibility for the overall reuse system. 942 General Design Guidelines. See paragraph 9312 for the pertinent information concerning the design of the aquifer storage requirements. Design aquifer storage requirements. Wells differ from the typical influent and disposal wells in several areas. The aquifer storage requirements wells are typically shallower than disposable wells, completely less saline receivable zone. 3. The aquifer storage returns wells are designed to maximize the storage recovery versus maximizing the disposable capacity. 3. Confinement to prevent fluid movement is not typically stringent since the reclaimed water quality is generally very good and because of the mode of the operation recharge of the recovery for a few areas of the typical effect of the aquifer storage recovery wells are installation of a pump and motor in wells since they are operated with the production of the well during the recovered periods. 5. A small above-ground storage facility may be required for an above aquifer storage recovery system to meet the diurnal variations of the reclaimed water demands. 6. Wellheads associated with the piping are modified to allow the bidirectional versus single-directional flow. Note that the aquifer storage recovery plunging issues with less concerned citizens. The aquifer storage recovery wells is periodically pumped as part of normal operation. B. In determining whether the design of the disposal system of the aquifer storage recovery system may be pre-designed should be evaluated. Generally include the minimum following criteria. 1. Analysis, reclaimed water supply and demand projections, including potential reuse of the customers, characterization, reclaimed water quality, native formation water quality, assessment existing groundwater users in an area capability using of recovery efficiency of the reclaimed water store of their reuse application, identification, suitable storage and disposal hydrogeological sequence. And 6. Permitting consideration, determining which of the program meets environmental objectives with the same set for the criteria. Section 10. Solid conveniency and solid pretreatment.